Okay, hopefully you can see my screen now. Thanks again for joining this morning. My name is Michael Koenig. I'm the project leader for Honda Smart Home. And as you heard, we're going to try this a little bit of an experiment this morning. Normally I'd come up and give tours to folks that are interested, and we can stand around and have some conversations. So I'm hoping the first half will be a little bit more traditional webinar, put your feet up and just listen to what we'll go through. I'm going to try and touch on virtually every interesting system in the house and our design strategies and philosophies behind it. So hopefully some of this will strike some questions in your mind. So please type them in, and we'll handle that kind of as standard webinar stuff. And then second half hour, we'll try and open it up for more free conversation back and forth. Now, the first question most people usually ask is, why did a car company want to build a house? And the answer is, we're interested not only in electric vehicles, but how do we get renewable energy into them? How do we expand renewable energy in general? And how do we integrate all that with the electric grid? And if you rewind the clock, 2012, we were thinking about this project and what are we going to do? And we were looking at California's 2020 goal, which said, hey, all new residential construction should be zero net energy by 2020. And we said, wow, that's great, but how is that really going to work? How could that come to be? And this house was in part an answer to questions like that. And so this is a 1,944 square foot single family home. We have civilian residents who live there. We usually change the residents once per year. They get the use of the house and also an all electric fit EV in the garage. And the project is zero net energy for the house and the transportation. And the thought here is we really like this image. We really like the idea of a future where everybody's got electric vehicles, everybody's got solar panels on the roof, but these are potentially two very disruptive technologies. And so how can we put these together in such a way that they actually create value for the electric grid? And by the way, let's do this in a way that actually respects all facets of sustainability. And so for me, when we were thinking about this project, it really comes down to these 5 elements, not just energy, but water and waste and the health of the occupants, and critically the materials themselves. And we really tried to focus on all of these during the project development and execution. So as you heard, the house is located at UC Davis West Village, and this is us. This picture is a couple years old, but there's a little bit more construction here on the north end. And we chose that location for a couple reasons. One of them is the environment is a little bit more severe than Los Angeles, where we are. It's if you're not familiar, it's kind of hot summer, dry, like desert climate, and a little bit chilly in the wintertime. But also, maybe more importantly, is that UC Davis West Village is intended to be a zero net energy community. And you can see all these solar panels on the roofs here. And that to us was interesting electrically. And so that was some of the reason for putting the house there. Now, like most zero net energy projects, of course, we started with the envelope. So how do we get our HVAC loads down? Spent a lot of time with the orientation, the glazing on the south side, the overhangs to block the sun in the summer and open in the winter. The walls are actually kind of thick. They're 9¼ inches thick, but they're actually double stud walls. So for the most part, to eliminate thermal bridging through the walls, full filled with cellulose, triple pane windows. And we spent a lot of time on the air sealing to try and make the air barrier as tight as possible. Not just conventional sealants, but when we were building this, the university was working to develop and commercialize this aerosolized sealant. And it's kind of neat. If you haven't seen it, you pressurize the house, you spritz this sealant in while the house is pressurized, and it finds all the gaps and cracks on its way out and kind of sticks to itself and seals the house. So that was kind of neat. And then actually the Western Cooling Efficiency Center helped us design all of the HVAC system. And let me clear this a little bit. So you can see there's 3 things I want to talk about today. One is the system itself is 100% radiant heating and cooling. So radiant heating is not so unusual, but radiant cooling is quite unusual. And there's some technical reasons we can get away with it. But it's neat because we activate the second floor ceiling. So we've got these hydronic tubes behind the drywall on the second floor ceiling, and also in the first floor slab. So we don't have any conditioned forced air in the house. We do everything radiantly. And that's driven by this neat 3-mode heat pump. So it's a small 2-ton water-to-water heat pump. It does heating and cooling and domestic hot water, all from the same super efficient little machine that is ground source. So it's coupled to these kind of interesting boreholes in the backyard. And one of the things that we can do, because it's an integrated system, and so here's that heat pump, it's just this little box in the mechanical room. One thing we can do is we can use regular electric energy to make hot water, or in what I want to talk about is during the summer, when you're cooling the house, you're really pulling heat out of the house. And so instead of rejecting that heat outdoors and dumping it into the earth, you can actually reject that heat straight into the hot water tank. And so we make quite a bit of energy, or quite a bit of hot water for free with that salvaged energy. And then in the back corner here, you can't really see it in this photo, but in the diagram you can see, we also have, it's called a drain heat recovery heat exchanger. So when you're taking a shower upstairs, you've got all that nice hot water running down the drain. We actually pick up that heat on the outside of that drain pipe and dump that back into the tank. And so depending on the year, we might see as much as 30% of our hot water comes for free. The boreholes themselves are also pretty neat. This was something the university wanted to look at because a lot of people, you've probably heard, ground source heat pumps are pretty efficient machines, but generally also pretty expensive. And a lot of that expense comes from the heat exchangers themselves, because you've got to drill these holes down on your property and then sink the heat exchangers down into them. And so the question was, hey, how about if we use boreholes that are only 20 feet deep, but they're 2 feet diameter? And so now you can drill these things with an auger like this. You can drill maybe 10 of these in a day. So it's much, much cheaper equipment and time to get these holes dug. But then into those holes, you're going to put 250 feet of coiled up heat exchanger tubing, drop it down in the hole, and then fill it back up with dirt. And the question was, how effective are these? And as part of that experiment, we actually have 4 boreholes that are dry, and then 4 of them are wetted. So we have this, it's actually culvert pipe, this big black plastic pipe lines the hole. And so we fill it up with water. And so it's actually the gray water from the house runs through 4 of these holes. We can pull heat out of there or reject heat back into there more effectively. And then that gray water will overflow to irrigation. And we published a paper on that effectiveness, if that's something that you're interested in. Here's what the panels look like upstairs. This is the master bedroom. And you can see the white tubes here are the hydronic pipes. They're carrying the heated or cooled water. The black pans are sheet metal pans. They're here really just to help move that more effectively into and out of the drywall. So this is obviously before the drywall goes up. And then that's what it looks like after the drywall was in place. And of course, since we knew that we were going to bump this out, we just put a nice little light feature here. Here's the first floor slab. This is concrete day. Of course, you can see concrete coming in, and it's actually a little bit thin. And we were able to thin out that slab in part because it's a post-tension design. So these straight black lines, hopefully you can see my cursor here, sitting on these black plastic chairs, those are post-tension tendons. So it saves concrete and saves steel in the foundation. But I wanted to point out the bent ones here. These are actually black plastic tubes, unfortunately black also, but they sit on top of this insulating mat, which is the insulation for the bottom of the slab. So the tubes here are down on the bottom of our slab, acting up. Part of the design strategy, the reason we can get away with this little 2-ton heat pump is because from the start, we knew we wanted to use the nice, cool evening air to pre-cool the house. And so part of the original design was we've got this nice big whole house fan in the mechanical room. We draw cold, fresh air in through a filter outside the house on the north side. And then all night we can push that nice cool air into the living room through these 3 registers in the living room. And then the original plan was we would open up these Clerestory windows and just let the warm air out. Honestly, we had a lot of trouble. They were third-party actuators. We had a lot of trouble getting them to work reliably and quietly. And so we abandoned the Clerestories, and we just moved to using the bath fans. So we've got 5 fans. We can command them to 50 or 150 CFM. We turn them all on, which of course depressurizes the house, which everybody knows is a terrible idea. And we proved that is a terrible idea. So then we moved on to a more balanced system. And what we've been running the last couple of years is we turn the whole house fan on and simultaneously turn on the bath fans at various levels to move. We get about 650 cubic feet per minute all night long to pre-cool the house. Now, the other big electrical system outside of HVAC, the other big system, of course, is lighting. And we started this with the viewpoint that when you come home, it should just be magically delightful, right? It should be this comfortable space, and it doesn't matter why, but it should be the space that you feel happy in when you come home. And daylighting is a big part of that, honestly, and it may or may not be the most efficient way to light a space, but it's comfortable for the human being. So we focused a lot of effort on daylighting. But then with the artificial lights, we worked with UC Davis, California Lighting Technology Center, to try to develop a system that was, first of all, really energy efficient. So all LEDs, which today is a little easier than it was 6 or 7 years ago. But all of those LEDs are also really high quality. Everything's at least 90 CRI in the house, and healthy, good for the occupants. And you can see up here, the tagline at the top here I wrote was, maximize the human experience, but minimize your interaction with the machines. And so what you see around the house is a bunch of these little dots here and there. They're motion sensors, they're daylight sensors. And we run the house in 5 different scenes, so 5 different times of day. It'll do different stuff. And the thought is it should just do whatever you want. If you walk into the kitchen at 10 o'clock and getting a glass of wine, you probably want a lot less light than you wanted at 6 o'clock when you were making dinner. And so we try to have the house respond intelligently based on the time of day, and just do it automatically in the background. If that isn't exactly what you want, we've got switches on the wall. You can just override it easily, because I think that's easy enough to do. But we try to avoid the situation where you have to go to the iPad or the panel and touch a bunch of buttons, because that's not the best experience. Now, from a health viewpoint, you've probably also heard that the human body has these natural 24-hour cycles, your circadian cycles, and that blue light, which is kind of prevalent in the brighter white light, the cooler colors have a lot of blue light content. That blue light tends to disrupt your body's production of melatonin. And so we wanted to try to respect that, and we actually landed on a pretty simple strategy, which is most of the fixtures in the house are fixed, warm, 2700K color temperature. We do actually have one array, the great big array up on the plant shelf upstairs is adjustable, and we'll run that a little bit cooler during the day and a little bit warmer in the evening. And then at night, we have, if you get up in the middle of the night to go get a glass of water, we have these deep amber safety footlights all around the house, so you can move around safely. And these are amber not just for your circadian rhythms, but also to respect the way your eyeballs work at night. Is they develop rhodopsin, and if you turn on white lights, you can bleach that out. So we try to keep your night adapted vision in place with these deep amber lights, so you can move around the house and get back to bed. And one other comment about the app, we do actually have a pretty full function app. It runs all the systems in the house, and that's really just because we needed it, not because I think that's the best user experience, but because we had the prototype HVAC system, we have the energy management system, we had this complicated lighting system, we ended up needing quite a lot of controls in the app. We don't try to force user behavior. So we'll never turn off the dryer or turn off the dishwasher to try and conserve energy, because this is the 21st century, right? Everything should be better. You shouldn't have to sit in the dark or push a bunch of buttons. That's our engineering challenge, is how do we make your life better, and just pick up in the background and improve things. And so we don't force anything, and we don't even actually try to coach people. I know there's a lot of smart folks working on coaching user behavior, and we generally don't do any of that either. But that's all I'll say about the app. We do have quite a lot of controls in the house, and we do have a pretty big app. So then, from an energy viewpoint, the last thing I'll talk about is, of course, this is the brains of the system. This is how the magic happens, because if we didn't have an energy management system, we'd just have a big solar array and a big battery in the car, and we wouldn't be creating value for anybody. So we have a 9.5 kilowatt solar array on the roof, which is pretty big for residential, but that powers the house and the car. And it's a DC system. So we have DC power, direct current power comes down from the solar array into the HEMS machine, home energy management system, the HEMS machine here in the garage. And that has a single 10 kilowatt bidirectional inverter, which means that we've got DC power coming in here. It can move DC power in and out of this stationary battery. It's a 10 kilowatt hour stationary battery. And also we have a DC car charger, a bidirectional DC car charger. It's only 10 kilowatts, but it is bidirectional. And so now this energy management machine can take this DC power and push and pull it in and out of any of these devices, and then decide how does it couple to the electric grid. So how does that inverter decide when it's going to make AC power to push out, or how it's going to do that? And because we have storage, that's kind of the critical factor here. Now that we have stationary storage and we have this dispatchable bidirectional load in the car, now we can decouple what the house is doing. And so, for example, clouds come and go and our solar power, waxes and wanes. We can automatically smooth that out. We can fill in the valleys with the battery power. We can listen for voltage excursions on the grid and respond automatically, or we can listen for requests for demand response events from the utility or third-party aggregators. We can decide when do we want to charge based on the lowest carbon energy on the grid. And so we can do all of that in the background. The user doesn't have to do anything. And the idea here is now, this system is what enables us to create value, and actually, instead of creating disturbance, now we're doing kind of proactive beneficial actions for the electric grid at large. Now, moving on to water, I mentioned the irrigation is by gray water. So when that water comes out of the boreholes, I talked about, it actually flows into this big green cistern in the backyard, and it just gets automatically pumped out. So we don't use any potable water for irrigation, just that gray water, and that's one of the biggest water savings in the house. But I wanted to call out, during the design phase, we were really careful to do what's called a compact plumbing design. And so compact plumbing means that you have as shorter runs as possible. So we've placed both the upstairs showers are right above the hot water tank, and right on the back side of this wall here is the kitchen sink. And so the thought here is, when you turn on your shower and you're waiting for hot water to arrive, as long as you've got to wait is how much water is sitting in the line, and all of that cold water is just being wasted. So by having really short runs, the user is happy because the hot water gets there quickly and you waste less water. And then of course we have dual flush toilets and low flow fixtures and everything else you'd expect in a modern house. From a materials viewpoint, we spent a lot of effort on a number of different angles, and a couple I want to call out, starting with the concrete. So you probably know concrete is rocks and sand and water and cement. And Portland cement is generally accepted to have about 1 pound of carbon dioxide for every pound of cement that's produced. And so we tried to reduce the amount of cement, first of all, by reducing the amount of concrete in the slab, but also we worked with the local concrete yard to develop a concrete mix that offsets 50% of the Portland cement with this natural ash, this naturally occurring pozzolan material. And then what you'll see here on the side is, this is actually our structural slab. It's exposed and it's polished. And the reason for us to polish that was two things. One is it helps our HVAC system work more efficiently because we don't have any floor coverings. And because we don't have floor coverings, we didn't have to go out and consume more materials. And we just have this beautiful slab exposed. All of the lumber in the house is Forest Stewardship Council certified for sustainability. All of the trim, all the furniture, everything is third-party certified. The insulation is it's actually a natural cork on the visitor center, which was just an interesting thing to do, but in the house is almost exclusively a recycled paper cellulose insulation. All of the furniture is it's natural materials, and critically, there's no formaldehyde and no chemical fire retardants for indoor air quality and health. And then of course, all of the trim materials, also everything in the house has a reason for being there. So we use several different countertop materials, for example, but they're all recycled materials. The hardware was locally sourced, the tiles were locally sourced. So everybody in the house has a reason that they're there. Now from indoor air quality viewpoint, I mentioned a couple things already, but it really starts with the walls. You need to make sure that the walls stay dry and we don't have any sort of mold or mildew growth inside the walls. And so in the design phase, we were really careful to think about the landscape strategy and the grading and make sure that we were able to take all of the rainwater away from the house through these rocky swales. And the water stays on site. It flows to a couple of rain gardens. So it perks down into the soil, but we keep it away from the house. And similarly, the siding is also what's called a rain screen design. So we have these furring strips here to gap the siding by about 1/4 inch. So after a rainstorm, a little bit of moisture gets behind the siding with that air gap. It's able to dry out and we don't have any moisture collecting and seeping into the walls. Inside the house, we have automatic humidity control. So we have these humidity sensors that will automatically turn on the bath fans whenever there's it senses that there's high humidity from taking a shower. And then we have a couple other things. Of course, we have a downdraft hood for the cooktop. We also have a whole house central vacuum system. And the thought there is, when you're vacuuming, let's get all that dust outside of the house. And so if you run any of these things, we'll automatically open up the fresh air damper, the damper that opens when we'd be ventilating the house at night, to let clean air in. It comes in through a filter and uses the makeup air while you're running any of those things. But what's neat is because we have so much instrumentation, we have so much control, we actually know when you're running the vacuum and we know how much air is leaving the house. And so then we can calculate and figure out whether or not we need to run more mechanical ventilation later by just turning on bath fans and bringing more fresh air into the house or not. And so, hopefully some of that's interesting, and hopefully you're thinking of cool questions and you're madly typing out questions as I speak. But when we were thinking about this project, we said, look, one big company doing a demo house, is that the best we can do? How do we move the ball down the field? How can we make this be more valuable to society? And we decided that the most impactful thing we could do is just make everything be open source. And so if you go to the website, homtosmarthome.com, we have all of our drawings are there, all of our specs are there, and they're freely available. Feel free to take them, as is all of our data. So we publish 239 channels of data at 1 minute resolution, which is it's a pretty good data set, better than you can find for a lot of these things elsewhere. We've got weather conditions, we've got soil temperatures, we've got all of the individual water flows, we've got circuits, slab temperatures. So for example, this is just some random day. This is what solar radiance look like minute by minute through the day. This is what the actual DC power look like. And you can see it starts to gap here once the panels start to get hot. We're down below, the blue line is what our refrigerator was doing one day. Everybody knows they cycle. How often does it cycle? Well, this is what our fridge is doing. And maybe this is interesting to you. You're certainly welcome to take any of this data. Or if you have a request or you're working on a project, let me know. And I'll say this, I realize a few folks on the call might be thinking about doing your own demo house. It is a real hassle to get it done. And so, this is that mechanical room, and obviously during construction, there's a lot going on and there's a lot of work to keep it running. So if you're thinking about doing your own demo house, definitely reach out to me separately, and I can help navigate some of the potential pitfalls. Or if you're in academia or industry right now and you'd like to use this data, but you want something slightly different, definitely reach out to me. We can see if we can get some different instrumentation in the house to help with that. So that's the end of the slide deck. Like I said, I'm hoping we'll have a few minutes here for kind of normal Q&A, and then we'll open it up. If people want to stay and just have a little bit more kind of fireside chat, we can unmute mics and dig into things more deeply just as conversation. Thank you.
Sounds great. Thank you, Michael. That was great. So we have a couple questions coming in. So I will go ahead and Emily, if you have availability on the phone, I will go ahead and unmute you. Sometimes the people call in, they don't have phone. So if that's the case, I will read her question. Emily, you're unmuted if you want to ask your question to Michael.
Yeah, let me know if there's feedback because it's just through my computer audio. But I was wondering
Sounds great.
Okay, awesome. If the house design and the airflow take into account California's wildfire season, and if there's a way to block off outside airflow or still maintain the temperature, humidity, and other operations that the house does automatically without pulling smoky air in?
That's actually a good question, because it's integral to the heating and cooling design is, if we don't pre-cool the house and it's super hot day, it's going to be hard to keep the temperature down in the house. And so we do have the option for the occupant to turn off the nighttime ventilation and the ventilation in general, just in case that situation arises. The one thing we don't do is we don't do it automatically. We don't have air quality sensors to decide to do it automatically, but the possibility is there. But like I said, if it's super hot, the system just won't be able to keep up. Eventually the house temperature will creep up over several days if it's too smoky to run the fans.
Thank you.
switches to both accompany indoor air quality as well as monitoring the VOCs and particulate matters in the house.
No,
So it's
oh, go ahead.
Anyway, so no, so anyway, it's a company out of Dublin, and I actually am one of the Panasonic Life Solution representatives, and we are launching a product called Cosmos, which is going to be an indoor air quality monitoring system.
Yeah, I saw that at CES.
So, yeah, so to that last question, I think her name was Amber. There's a system that we are launching just here in a couple months that will monitor and actually work with some ventilation and air exchanges. And you might see one of my other questions is, are you using an ERV for some of that air exchange? Because our ERVs actually use a MERV 13 filter. So with the wildfire concern in the state of California, this might be something to look at. And if you're interested, I certainly would love to pass my information on to you.
Yeah, well, yes, that's actually two separate really interesting conversations. And for sure, if you wanted to send me your contact info, I'm always interested to talk to your guys. To the indoor air quality, in retrospect, that was one of the things that we missed. We have indoor temperatures all over the house and humidities, but we didn't put in other indoor air quality sensors. And so for a little while, we did run a third party, the little box you can buy and put on the shelf. And so I have a little bit of that data for a small period of time, but I don't have really good data on indoor air quality. So that was one of the things that I would have wished we'd done differently. But to the question of like dew point control and condensation, what we do is, because we know temperatures and humidities, we know what the dew point is. And so the first floor slab is not a concern. I don't think we have the capacity to cause condensation on the first floor slab. It's Davis in the cooling season is quite dry, and so that's why we can get away with the system, is that there's not a lot of humidity to contend with, so we don't even have a dehumidification system in the house. But we do have to watch the second floor drywall. It would be possible to condense, and so we do have controls there. So when the temperature of the drywall gets close to dew point, we need to turn off the upstairs loop and let it come back up to temperature. The ERV question, that was one of those things that came out in the very initial design phase, because everybody knows a couple things always pencil. Everybody just knows that solar hot water should pencil and that an ERV should pencil. But in our case, at least at the time when we looked at the numbers, because we were doing ventilation at kind of preferential times of day, we were taking cool air in instead of hot air most of the time. The additional fan loads of the ERVs didn't pencil for our house. But I do love, I've seen some of the small ERV and HRV systems that just kind of fit in joist space. I think those are fantastic designs. They just didn't pencil here because we were so carefully controlling when we were ventilating anyway.
Great. We have a somewhat related question here from Don. He's wondering what type of sensors were used in the wall for detecting humidity.
I don't know the brand name. I don't know if they're called out on the documents that are online, but if you've got specific questions about that, definitely just send me an email and I can connect you with the folks that did all that instrumentation. And they're actually they're a great outfit, and they're still doing data monitoring for me, and they'll be able to answer any of that.
Great. And then we have a question, and we were talking about this before we started the webinar, about who's living in the house right now. You had mentioned that it changes kind of on a yearly basis. So we have a question about who might be living there now.
Yeah, so we generally don't publicize actively the names of the folks. We've done a little bit with that through the years, where we had some interesting people and we made a video with them, but just to respect their privacy, we usually don't, kind of publicly announce. But I would say that actually right now, the current occupants moved out a little bit early, and so the house, as of right today, is vacant for the next couple months until the next occupants move in. But by the terms of the land lease with the university, we have has to be faculty or staff or grad students live there. So they're civilians, they don't work for Honda, but they need to be associated with the university in some way.
Great. And then we have a question from
Sorry.
Claire. Oh, go ahead.
I'm sorry, I probably should have said there. By the way, if you're interested in living in the house, if any of the folks are actually at the university, we try to put out a call every January or February timing just to remind people to apply. And so, you know, if you're interested for next year, definitely just look for that.
Yeah, and if you're interested in, again, our mailing list, we definitely push that announcement out to our mailing list. So feel free to join that, and then you get that announcement and can keep track of the application timing. We had a question from Claire about kind of your position on retrofitting homes. You talked about how difficult it is to do a lot of this, and kind of what does that mean if you're retrofitting?
Yeah, you know, I kind of just punted on that, honestly. You know, new construction is so much easier to do all of this, and I've looked at that a lot because it's, you know, what is it, 80 to 1 or something, right? There's got to be 80 million houses in the US when we build maybe 1 million a year. And so clearly the existing housing stock is the long pole in the tent. And I would say that that's the challenge. And I don't know how to solve that so much. You know, if you don't mind going slightly astray here, HVAC and hot water, you know, that's always a little bit hard to retrofit, or you know, home house energy package is a little bit hard to do. I would say that from just managing the energy and you know, if you're getting an electric vehicle or something like that, there are a couple things that can be done. And we have been looking at, you know, as a company, the idea that you would have small energy management machines in your garage. Clearly what we've got here is a pretty big, expensive system, but we've been looking at much smaller versions of that. You might have seen a thing called the Honda Power Manager, which does some of these functions in Japan. And if you want to do some of this stuff on your own, you know, meaning at your own house, you know, there are some products like that on the market. But I would say that at the larger level, it is so hard to do energy house by house that one of the other approaches that a bunch of companies, you know, auto OEMs and other energy companies have been looking at is, let's just step back and look at the millions of cars on the road and aggregate what we're doing with the cars. So for a long time, you know, electric companies have turned water heaters on and off, or air conditioners on and off. And so as we get more and more electric vehicles on the road, that becomes a really powerful way to create grid value also. And I didn't touch on that at all today, and I know that wasn't exactly your question, but I just wanted to mention that that's also a really interesting field of study for people that are interested in kind of the macro energy shifts that can be done. But to your actual question of retrofits, that is tough, and I haven't had any experience or luck going down that path.
Thanks, Michael. And then we have a question from Kevin. So Kevin, if you're available, I'll unmute you. He has a question about interconnection for bidirectional electricity flow. So Kevin Jensen, I'll go ahead and unmute you here. All right, Kevin, are you available? Let's see.
Yes, hi, can you hear me?
Yeah.
Okay, hi. Yeah, I just had a question about the energy management system. You know, interconnecting solar bidirectional stuff is, you know, common, but in this system where it's interconnecting the house and the car and back and forth with the grid, is there any special considerations with that, or special approvals, or how did that happen?
Yeah, so this starts getting pretty wonky pretty fast. In our case, we got lucky right at the time that we were interconnecting this. There was a ruling that said as long as your battery was 10 or 20 kilowatts or some, you know, below some threshold, you could interconnect it just with the regular kind of solar interconnection process, and that's what we did. So we did have to get in situ certification by TÜV. You know, obviously the device isn't a mass production device. It was TÜV, I think it was TÜV who did it. You know, for the most part, you're right. If you were going to interconnect, you'd need to be UL 1741 SA compliant for most of these things. So right now, you certainly can do that. But one of the tricks is our vehicle is DC based, and so that means that the inverter is on the, you know, on the structural side, and that's what makes it easy and possible to do. AC bidirectional interconnection right now is not clearly allowed unless you had a UL listed inverter in the car, and you know, nobody's actually done that. So AC interconnections are really challenging. There's a proceeding going on right now to try to figure out how to do that in the future, but DC is possible.
Thank you.
Great. And let's see, this is a question from someone without a microphone, so I'll go ahead and ask that. He was wondering if there's any newer technologies you would use now if you built another house. Technologies that you are confident would work well instead of something to try. So something that has, you know, good standing or likelihood of succeeding.
Yeah, that's a good question. Usually it comes down to the like, what would you do different? And I think for sure we would do something different with the lighting system. Let me see if I got a hidden slide in here. Let me see if you're still online. I can try and show you one thing. Our lighting system ended up, you know, again, this is several years ago that we did this, and hopefully you can see this. So the actual lighting system is pretty efficient. It's this was a few years ago, 1,100 kilowatt hours on the year, which is, you know, 44% less than the average new construction. Great, except if you look at the line above it, the control system, you know, which of course this is controls for the house and the car and the HVAC and the lighting, but our control system uses more energy than the lights do. And so for sure, if I was going to do this again, I'd try to use more modern, actually even just some of the Wi-Fi light bulbs. I think I haven't seen a system that does exactly what I want, which is lots of different scenes at different times of day, because the standby loads are killer. And if you think about, obviously this is the accumulation of all of the standby loads for our controls, but if you think about even some of these little standalone, you know, fancy switches that run your Hue light bulbs or whatever they do, even if they're just 1 watt of power, there's 8,760 hours in a year. That's 8.5 kilowatt hours of energy from that 1 watt draw. And 8.5 kilowatt hours is more energy than the car uses in a day. So every watt of standby power is 1 day of free driving the car. And it's really, you know, that's what you need to really keep in mind. The standby loads just add up. And so you need to make sure that, you know, whatever systems you're using are as efficient as possible. But I do think the lighting systems, for sure, there's better stuff today than what we used. And honestly, you know, if I was going to talk about the HVAC system, I would probably try to use a little bit more intelligent controls and get by with ducted mini splits, multi splits. I think that, you know, those systems are really efficient, and there are just so many potential drawbacks with the radiant cooling. I know that there's some smart folks at Masana or other places that are doing that as their business and have good success. But if I was going to do it again, I would probably go with a little bit more conventional air-based system. But other than that, honestly, a lot of the stuff in the house is working really well. I'm pretty happy with a lot of the equipment in there.
Great. We have a somewhat related question. And you mentioned that I think that this was the cost of most of this stuff, since it was kind of cutting edge, was a lot higher at the time when the house was built. But someone was wondering what the cost for the house kind of was, and if there have been any challenges in kind of sensor monitoring that's happened since the house has been built.
Yeah, so because it's an R&D endeavor, we don't disclose the cost. So I can't get into detail there. You know, system by system, some of the folks, for example, the guy who did our those panels you saw upstairs, the radiant heating cooling panels, he claims he can do that system for the same or less money than a forced air system. And so system by system, it may or may not have been more money, but you know, you could see that the piping, here we go. You know, if you look at this system, this is our heating and cooling. You know, there's obviously a lot of money went into all of this custom design and installation. So I can't really get into that. Apologies. The sensors, for sure, we've had a lot of, well, I wouldn't say a lot, but we've certainly had a number of either sensor failures, or sometimes they were just damaged during the original installation. Keeping the data loggers logging accurately and uploading, you know, continuously has been a little bit of an issue. But for the most part, like I said, the company that's been managing that for me has stayed on top of it, and the data loggers have enough buffer that you know, if they go down for any period of time, we don't actually lose the data. So anyway, I'm happy to talk offline if you have more specific questions about the data logging and connect you to those guys.
Great. And then we have another question. Someone wondering if you think a Tesla car and a Powerwall could be worked into kind of a net zero energy system.
I think for sure. And then the only question becomes, if you're talking about being off grid or staying on grid, because you don't need a power wall to be zero net, as long as you're grid tied. But then if you're off grid, it becomes a, in our climate, it's actually not bad, because there's only a few days a year where you're getting relatively low solar generation day after day. It's pretty rare. And so with our big solar array and 10 kilowatt hours of storage plus the car, we can get by. Other places you probably need several power walls to have enough energy to be confident in that. But for sure you could do it. But then the question is, if you want to participate and do the grid services like we're doing, the question becomes, why are you doing it? Because keep in mind that the battery and the inverter is going to have some round trip efficiency loss. You might lose 10% of your energy taking it in and out of the battery and converting it twice. And so why did you just waste 10% of your energy if you're not getting paid for it? And in a lot of places, in basically everywhere, that's the pig in the python. Is it's hard to monetize it. It's hard for the homeowner to make money on it. Certainly, if you've got a high time of use rate, there are folks that are using power walls to reduce their bills, just with what's called load arbitrage. So charge it up when it's cheap and then discharge it when it's expensive. But it's a pretty big investment. So it has to make sense for that individual homeowner. Just as a time check, do you want to move on to a free conversation, or do we have a lot of questions? I'm happy to go either way.
Sure, I have one more in the queue, and then
Okay.
I think that's a great idea.
Okay.
So we have a
folks
question.
are folks just gonna like raise their hands, and then you'll unmute people who raise their hands? Is that what we want to do? Or?
That sounds great. Let me start with unmuting Angela. She has one question here, and then if you have a question, we'll just kind of open it up. You can just raise your hand and we'll unmute you. So let's see, Angela Jones. Hopefully I'm pronouncing that. Go ahead and if you'd like to speak, you are unmuted. Oh, Angela, maybe, let's see. I will go ahead and ask Angela's question, just give her a chance. She may have stepped away. So could you describe the process that you go through to research and test various systems and our product material options, and then arrive at the one that is the best for installation?
That's a pretty open question. And so I would say that for a product development, if I was developing a Honda product, then there's a very specific way that the company goes through that R&D process. Obviously that's not something that we disclose, but there is a very specific way to make sure as you step towards production that it met regulations and met all your team targets and everything else and quality. But I would say in the case of the smart home, we were taking off the shelf, and I think this was the question, we're taking off the shelf materials. And so for example, we use one particular type of recycled paper countertop. And the question is, well, how did we decide that was the right one? I had the luxury of being able to hire a couple of really good interior designers and had them run down all of the specs on everything. And so for the most part, we didn't have prototype materials in the house. We had several choices for countertops, and we vetted them and came to the conclusion of which would be the most sustainable and the one that best fit with the concept. For the truly experimental stuff, like the HVAC system, again, we tried to use as much off-the-shelf equipment as we could. But in retrospect, this is one of the things we should have done better. Is we did not actually create like a hardware in the loop simulation, which we should have done. We should have done a hill simulation and taken some of the HVAC hardware and properly vetted all the controls, because it's, in my experience, at least with this project, it was less about hardware limitations, right? Because it's this nice Bosch heat pump and these nice, electric pumps, and all of these bits are individually sound. They're mass production products. It's the controls that's hard, and so that's what really needed more vetting before we launched the house. So we left ourselves 6 months of in situ commissioning before we had our first occupants installed, and we used every bit of that trying to get the controls functional, because that was our first experience to try and run things. And frankly, we should have taken more time than that even. Hopefully that answers the question.
Yeah, so at this time, if you have additional questions or want to talk about something in depth, we've got about 10 minutes left, so please raise your hand. I've gotten a few questions. We will definitely email, as long as it's okay with Michael, we'll email out a recording of the presentation as well as his slides. And then, he provided his email address and I put it in the chat box, so you're welcome to follow up with him if you have more questions as well. So I'll keep a lookout here for any hands that are raised. I guess while we're waiting, Michael, I had a question. I was wondering, so the house is about how old now? 9 years?
We started construction in 2013 and finished in 2014.
Okay.
So yeah,
So
we've
you
had
haven't
occupants in there over 5 years.
any maintenance issues yet? Or I guess I'm wondering what happens if something leaks, or, because it's so intricate. I guess I was just wondering from a maintenance standpoint.
Yeah, so we do spend a lot of time making sure the house is always in good shape because, it's a reflection on the company. We want to make sure that it's always kept in top-notch shape. I had a slide in here, I think I deleted it, which was we haven't had many maintenance issues, in part because, we're just out there all the time to make sure everything is kept clean and kept, functional. But the hot water tank, this is just kind of an interesting sidebar lesson, is in our original design, we had a very, very clever layout, and it's actually, you can sort of see it here. This pipe that comes from the top of the hot water tank actually comes back down and into the side of the hot water tank. And you say, well, why is this thing piped into itself? It was a very clever design that we were running we were trying to stratify the tank. And so in order for that de-superheater to work more effectively, we needed a larger temperature difference. And so we said, well, we can get a larger temperature difference if we can separate the heat energy that's in the tank, and we can keep the top of it hotter and the bottom of it cooler. And so we ran the makeup water through a coil in the bottom of the tank before it dumped in there. And the thought there was, hey, this will be really smart. We'll stratify the tank. So de-superheater works, but that coil that we were using in the bottom of the tank was originally designed for a solar application, and it was just a plain carbon steel tube, and it failed after about 5 years, which was very unexpected, and we had to replace the tank. So just kind of a sidebar commentary that be very careful if you're doing any project like this and you decide to go off label, because obviously it was a mass production tank. It was not an experimental piece, but we just used it in a slightly strange way that the manufacturer hadn't anticipated, and we caused it to fail. But no, we haven't had a ton of other failures at the house.
All right, well, I don't see any hands raised. And I have to say, I have never seen a cleaner garage in my life. I would love if my garage could look like that. It's very inspiring. All right, any last questions? And we will wait a second for any last questions. I just wanted to thank Michael for joining us and giving us a great virtual kind of experience of the Honda Smart Home. Yeah, absolutely. And again, thanks everybody who spent your time with us this morning. It's always a joy to get to talk about it. And so if you have more detailed questions, or you're doing something a little bit funny, or you want to see if the house can do something for you, like I said, definitely just reach out to me, send me an email, and check out the website. We've got a ton more videos on there, kind of layperson's videos, and obviously all of our data and drawings on there also. Oh, we have one more. We have a raised hand here. All right. I hope I'm pronouncing it right. Akshi, I will go ahead and unmute you. Okay, you should be able to speak.
Hello.
Yeah, hi. Is it Akshi?
Hi. Yeah, am I audible?
You are. We can hear you now. Yes.
Okay, great. Yeah, thanks, Michael, for the presentation. It was very interesting. I was actually around in Davis in 2013 when this was going on. So it's great to see it being in function and in use now after so many years. I had a quick follow-up on the sensors that you said, which had a little bit of troubles. For instance, like how does a change of sensor work if it malfunctions? For instance, and I mean, how long is that? How long does the procedure go to change it? I mean, and what kind of sensors have been found to be more prone to, have to damage?
Gotcha.
So if you could cover a little on that.
Oh, sorry, go ahead.
Yeah. I just wanted to see, get some more perspective on sensor performance.
Yeah. Again, I'm going to have to defer a little bit to the folks that are still running that, because they're the ones that spec out most of the sensors, and they have a lot of experience with, whether it's resistors or thermocouples or whatever for different types of applications. And so if you send me your contact, I can definitely connect you with them for some of those questions. But I would say that at least in this case, because this is still it's a prototype conglomeration of components. When we, for example, we wanted to change out the motors, the original pump motors that we had for circulating were a little bit loud and a little bit inefficient. We changed them out, but the new motors had slightly different controls, and the long lead times are always getting the controls sorted to work with the new components, more so than like the physical changing of the sensors. So we have sensors, for example, embedded in the walls and in the floor, but there's very few of those that we actually use for control function. Most of those are just for data logging. So I would wager we probably only operate on a dozen, 2 dozen of the 200 sensors. And so, if one of them in the wall fails, it doesn't really impact the operation. But when we do change sensors or hardware, it's always the controls is the longest lead time. And so for us, that's one of the things that we need to keep vigilant. So we always have a programmer available to sort things out in case something fails or something malfunctions.
Right. Okay, great. Thank you.
Oh, you're welcome.